All right, everyone. Welcome to another episode of AI Rewind 2021. Today, we are joined by Zachary Lipton, an assistant professor in the machine learning department and operations group at Carnegie Mellon University, to talk through all things machine learning and deep learning. Zach last joined us on the show for the 2019 edition of Rewind, and I'm super excited to have him back once again. Zach, welcome back to the TWiML AI podcast.
Cool. Thanks for having me, Sam. Great to see you again.
It is great to see you again. I think the last time we physically had the opportunity to hang out was also 2019 in Vancouver. I think that's probably a story shared by a lot of folks in our field. Like that was the last opportunity that folks had to hang out in person.
Right.
How have the last couple of years been for you?
Oh man, it's been eventful. Um, I'm not gonna pretend it's all been smooth, but I mean, some things are nice. Like my students are great, and I think it's not been easy for everyone. Like some people got sick, some people lost someone, some people didn't get to see their family for a couple of years. Um, they've On the other hand, like people, I feel like it's a weird thing where people have managed to be startlingly productive, or at least, maybe I don't want to shame anyone who doesn't feel productive, but I feel like from just my feeling of my lab, I feel like people are, and maybe it's just kind of a bit like CMU culture or something. I feel like people have been really, um, yeah, like locked in research, but I think there's a kind of like emotional wear and tear of just not seeing anyone, like especially like some folks are like living by themselves, and then like when they were in quarantine, it's like not seeing another human for 6 months. And I think for others of us, it's like catching up now. So it's been a little bit wild, but interesting on the research side, and we got a puppy, so like interesting personally.
Nice, nice. So, as I mentioned in the lead up, we are here to review the year in ML and deep learning. This is the third rewind that we'll publish. The first couple were in NLP and computer vision, or computer vision and NLP in the order that they were published. And so far, a couple of key themes have emerged. One, which was common in those first couple of episodes, is this idea that as John Bohannon put it, NLP eating machine learning, kind of like in the same way we would say, AI eating the software or what have you. The idea that computer vision is adopting transformers and things like that. You have echoed one of the other observations that John made in that NLP conversation, and it is that particular point is kind of a slowing down of the field and a little bit of a respite from that kind of breakneck pace of change that we were experiencing for a while. So maybe that is a place for you to jump in and riff for a bit. What,
Yeah,
what's your take
happy to riff.
on
um like, just since maybe I'm maybe like token a contrarian or something, I'll start by maybe pushing back on one thing that's kind of interesting of like, that phrase of like NLP eating ML is kind of cute because it's sort of, well, among other things, right? Like in some sense, there's like the line for the longest time, for the last 7 years, has sort of been machine learning eating NLP. And that, like, if you look at the set of
that?
people going into like sort of NLP oriented like grad program, there's a point where like NLP sat really close to like, they were like NLP and computational linguistics are like sort of two sides of a coin,
Uh-huh.
and they sat not so far from their like philosophers of linguistics or whatever. And now you have a moment for the last however many years where the median person in NLP knows absolutely nothing about language, has nothing interesting to say about language, that couldn't just as easily, and it's not to say nobody or that there isn't anyone with something interesting observations or interesting experiments that are kind of hitting on both sides, but to say that like the center of gravity of the field has moved to this way that almost there's almost no L in NLP. It's just like
Yeah.
it's just sort of like a set of tools where if the like commercial demand was more on music than on NLP, you would use almost, conceivably like the same set of models, because all they care is just like a sequence of tokens, like a very generic sort of approach. And so in some sense, it's sort of just been like deep learning eating NLP has been the story for a while. And I think that like this version of NLP eating ML is, well, I guess one, they don't really mean ML, but really more just like other application areas.
Yeah. Yeah.
I think,
And they don't
there,
really mean NLP as much as the thing that ate NLP, which is transformers.
right, whatever is like that like new organism that displaced MLP is now coming across. But right, it's more like, there was like a discipline of computer vision where you had people that like the typical person who was in there knew something about like the physics of light and optics, and like was sort of like doing this sort of like, that was the angle. They were like a real expert on like the modality of vision, and the person in NLP knew something about language. And I think
Yeah.
they both got ate by deep learning in such a way that, over the last 7 years, ideas that would hit on one side could very easily port across to the other. And
Mm-hmm.
for most of that history, I think it's hard to say precisely why, if there's some reason, or if it's just sort of the order in which things happen. Like, cause like those breakthrough ImageNet results that really caught people's attention were in vision first. But I think for most of that history, it's been very one dimensional, like very one directional of, I think things going from, you know, mostly in the direction of computer vision to NLP. And I
Mm-hmm.
think if anything, this is not really NLP eating vision, but it's just notable that maybe one of the bigger things happening in vision is crossing in the other direction, like contrary
Mm-hmm.
to the pattern.
Yeah.
But yeah, broadly on the like things slowing down pattern, I think I've been noting this and writing about this for, I don't know, maybe like 4 years now. But I think there's definitely a moment where, like, if we were to look through the history and say like 2012 ImageNet, 2014 like sequence to sequence models, 2015 AlphaGo, 2016, 17 big advances in like the kind of like uh, perceptual quality of like generative models, 2017 Transformers, 2018 BERT. There was a kind of change that, I don't think these are necessarily all profound in the sense of like some big intellectual move, but they are like qualitative changes in capabilities. There's a big move in the sense of like, what set of problems do I think are best tackled with these tools, and what sort of performance can I expect from them? And a big difference in the sense of, if I'm a practitioner in the field and somebody hits me with a typical like industry problem, what's my go-to tool? And if we look at like 2021, and now we're saying, well, if someone hits you with a classification task, what are you going to do? It's probably just going to use a ResNet from 2014, 2015. Someone hits you with an NLP task, it's like basically fine tuning BERT, or a BERT like, very Roberta, Alberto, whatever. It's like, right. Like there's this moment where, you know, um, I think that in some sense, I think it's okay in that, like researchers now need to like start looking somewhere else other than just like, what if I tweak the architecture a little bit? Like there's and as I was telling you, like when we were riffing before, is that I think that research is, there is some aspect of people like groping around in the dark looking for a way in. It's almost like they're like swinging at a pinata with a blindfold on and trying to find like where's there an angle that, like, where's there something big. And I think you want to have a lot of researchers in that mindset of like, I'm looking for the blind spot, like I'm looking for the big prize that other people aren't looking for. um, and look, every now and then someone really lands a mark, and the pinata rips open and a bunch of candy falls on the floor. And then everybody rushes on, and there's some period of time where nobody is worried about, like, nobody even knows where the bat is. Everybody's just picking candy off the floor. Um, and I think we saw that period of like people finding all these, it wasn't like you didn't need a big intellectual breakthrough to have to have an impactful breakthrough uh, in all those years. And I think we're getting to the point where, like, there is some amount of stagnation, because like most of the good candy has been picked up, and people are like looking at the old grimy like moldy stuff that's like, maybe there's still something in there. It's like like the sloppy seconds on the research, pinata.
With that analogy in mind, where should research be swinging the bat? Do you have is that it? It's a crystal ball kind of question, but what does your intuition tell you where opportunities might be?
Well, I always look for, what is it that we actually care about when people are selling a story, an aspirational story about, um, like, I'm not like a mathematician first. I'm not just like, what's a hard problem? Like, let's just solve it for that reason. I got into it too late. I kind of back into it from like, what's actually like, what's the dream? And if you look at like the dream people are selling people, even people with like existing companies right now, the claim they're making, like if you looked at like IBM Watson, which went up in flames, if you look at the claims they were making, like, what are we going to do for you? It's like, you're going to make better decisions. You're going to provide personalized healthcare. You're going to help people to have better health outcomes than they otherwise would have without our AI. If you look at this kind of stuff, what are people selling? What are people hoping to actually achieve? And then you look at like, what are people actually doing? And if I always kind of look back and forth between those and say like, what's like the missing part? Like if you actually want to realize the dream of what people just seem to want, what's gone? Or like what's not even being addressed in a mature way? And so I think one thing that sort of jumps out is that everybody's sort of premise, everyone says like these things are good. It's always based on some notion of like accuracy or the return of an RL system as evaluated on some fixed static environment. And then you look at what people are actually doing. It's like they're taking some model, trained in some context, on some set of data, and deploying that crap in some different environment, which is changing in unpredictable ways. And where the whole environment is not just changing like in a kind of benign or passive way. Often it's changing in direct response to like think about Google search, right? You deploy Google every single time they tweak their algorithm. What's the first thing that happens? And it's like all the message boards light up, and all the SEO
Right.
goons are like, oh, like SEO changed the algorithm. Now you need to add this keyword. You need to do this. And I think that ML doesn't address that kind of stuff. Like when I say ML doesn't, I don't mean nothing that we aspire to in ML, but I mean like the main thing, the main thing that practitioners do, the toolkit, the mature one, the like, I know how to use PyTorch and train, ResNet and ResNext and whatever. That world, it's like completely set in the environment of like, I train a model, evaluate on a sort of like IID holdout set, or even if you evaluate on some kind of challenge set, it's not like with any coherent principle for why you should expect this model to do well on that challenge set, or why you should think the performance on that challenge that's representative of what you should encounter in the world. So I think performing in a dynamic world, making decisions and not just predictions, right? Because everybody's sort of saying, ultimately, if you think you're going to make money off of this, or you think you're going to affect some kind of like societally beneficial outcome by using AI, if you think you're going to do anything, then ultimately it's like the claim at some point, what you're hoping to do is guide some kind of decision or automate some kind of decision, right? You're actually hoping to have an outcome, not just to like be a passive observer to the world and make accurate predictions about what would happen were you not to take any action at all. And this kind of setting of like actually providing guidance for what you should do in the world is we are, it's a thing that like, yeah, there are people working on causal inference. There are people who are trying to bring reinforcement learning closer to the real world by, maybe incorporating some ideas from causal inference, like to think about confounding that might exist in the data, to be able to build models in an off policy kind of way, so that you're not just saying, I'm just going to deploy some randomly acting system in an important application and have it suck for 2 million years until it learns. But they're relatively mature, and they get relatively little attention. If you were to look at like, what do people, what is, and not to like beat up on our buddies in the press, we say, what is like, Cade going to write a big article about in the New York Times? It's not typically like the slog of like scientific advances in making robust machine learning, or off policy RL or something like this. It's the there's a big neural network that has 9 trillion parameters and $1 billion investment from Microsoft and this kind of, and so I think decision making, robustness in dynamic environments, and actually addressing certain societal desiderata. People have sort of noticed the problems that arise in terms of the ways sort of like an AI system can affect, whether it's like unethical sort of outcomes if you plug them in naively into certain decision making systems, but the sort of like field of actually like developing systems that could in some coherent way align with societal desideratas is quite primitive, right? So there's like a recognition that there's a problem, but we're very early stages on getting towards solutions. So I think that, to me, like, these are the areas I think are more interesting, um, in that, like, look, if you can squeeze half a point out on, like, all the NLP benchmarks by like making a slight variation on BERT, you'll get a lot of citations that everyone will use it, and they should, and it is useful. But I feel like not. It's like it's like a slight change in degree. It's not a change in kind. And so I think, when I look at it, the field, I think the luxury of being in academia, the reason to be in academia is to think that, like, I don't have to just think, how do I do epsilon better than someone at the same crop we're all doing tomorrow? But like, what actually is something that, addresses, some problem that nobody's even engaging with intellectually right now.
It sounds like your answer then to the where to swing the bat is in getting closer to real world problems that folks are having. And you mentioned a lot of different elements. I heard some aspects of domain generalization in there. I heard, aspects of even like user interface, like how you're presenting the information. Heard aspects of fairness in there, but broadly, it sounds like you're kind of also calling into question kind of the simplification that often happens in research of problems that removes them from all of the constraints and fuzziness of the real world.
Yeah, and like, it's tricky, right? Because everybody's
Everybody thinks they're doing that.
well, it's more like everybody's got to choose to focus on something,
Mm,
and to focus on the thing they want to focus on, they got to compromise on something else. Um,
mm.
and it's not that like one thing is right or wrong. Like, I don't think it's wrong that there's people out there building bigger language models. I don't think that's fundamentally wrong. I think you got to be like, um, maybe like you got to use your brain to think about how what kind of claims I can make about these things, or how should they be used in the real world. But I think, like, look, it's interesting to turn that knob and say, what if I make this bigger? What happens? Um, there's plenty of work to be done. Like one kind of like trade off that you often have is that, um, you have like, if I want to get close to what real data looks like, and I want to get close to things I can actually do in a bunch of domains. Often, like, all that's available is, data's, like, there's a way that like predictive modeling and like the status quo, is closer to the real world in that it touches real data, and it gets within its like narrow aspiration of like just predict well on like IID data, like under a naive assumption about how the world doesn't change. It's able to do that on really complex, high dimensional real world data. On the other hand, what you give up when you focus only on just that problem is any kind of consideration of, I think people just only think about how do I get better at building predictive models, um, is, like, they're getting close to like the dealing with real data, but they're asking a very narrow set of questions about it, which is like, how do I get higher accuracy? Then on the other side, you have folks, say, for example, trying to get at like, fundamental questions about, what sort of like causal queries I can make. And very often, in order to flesh out those questions, now they're taking on like a more ambitious set of like kinds of queries that I can ask. But in order to make progress on like understanding the fundamental form of those questions, it often starts with, well, I got to analyze like fundamentally when are these questions even answerable from the data sets that I have. In order to like maybe get some of that analysis to go through, I have to make some simplifying assumptions about the form of the data. Like, I assume that the whole world is linear and it's not high dimensional and it's not whatever. So, you have plenty of people who are doing, work that's like really more like ambitious and expansive on the front of like the kinds of questions I can ask, but they're making really simplifying assumptions, in terms of like the source of data I have and the number of variables I have, and not worried about that for the time. And that's the compromise they make. And there's other folks building predictive models and trying to get close to like do something that works on real data, but be naive about the kind of questions you can ask, and not worry too much about just how limited is like what you could do with those predictions or their power to guide decisions in the real world. And then I think once you have that kind of tension of like, okay, everybody's looking at something and not looking at something else, I think the question you have as like a research community is like, are you over leveraged somewhere? I think oftentimes people, there's like a naive form of a criticism, which is like, oh, this thing sucks and this thing's good. But like there's a more mature version of it, which is like we're way over leveraged on this thing and paying way too much attention to this thing and neglecting these other things. So it's like, like more a matter of like moving the needle. It's not that like nobody should be building a bigger language model or tinkering with architectures, but it's sort of like, okay, like we're at a point where we're not getting nearly as much juice per squeeze doing that. Why do we have 99% of the community engaged in this? Why do we have so many papers that are being submitted that most of which are not actually contributing anything either as an idea or as a result? And so yeah, I think we're sitting in like some funny terrain like that.
So, were there notable papers or research advances that you think kind of poked at some of these issues that you're raising, or you think are swinging the bat in the right direction?
Yeah, I think there's well, there's a very weird climate now, which is like I think for a lot of these questions, you have sort of like like uh, a growing recognition that they're problems, but then you have like a subset of people that are just kind of like taking advantage of the way in which the like peer review system is like overtaxed and scattered, and like sort of just using the language of those problems but not actually addressing them. And I think you see this in all of these. I think you see this in the fairness literature. I think you see it in the robustness literature. I think you see it in the causal literature, like in that like people submitting papers that sound like they're addressing causal problems. They're not actually. People just saying this model's robust in a way where it's like, by the way, you can never just say a model is robust. Like if you state nothing about the ways in which the environment's allowed to change, and you know um, there's no such thing as like general robustness, right? Because I can pose two different assumptions about the world where in one of them, when the environment changes, and this is what I should be doing, and the other one, when it changes, that's what I should be doing, and I have no way of discerning which world I'm in, right? Like class would be like, do I live in the label shift assumption? Like if I make that assumption that like the distribution of categories is changing, but the class conditional distribution, what does COVID versus not COVID look like is what's not changing, but the prevalence is changing. First, do I assume that like the covariate distribution is changing, but that the label, the conditional, the probability of the label given the inputs is different? I might have no way of discerning whether I'm in world A or world B. But one thing is the right, like the robust model in this setting should do this, and the robust model in that setting should do that. um, so you have like a set of people that are just kind of doing the deep learning thing, which like prediction lets you get away with it, like let me throw spaghetti at the wall because I get to evaluate on the holdout data, and like how well I'm doing is identified, so I don't have to be able to state in terms of any principle. If you get to like a causal effect, you don't get to observe the causal effect. So it's like if what you're doing doesn't actually identify the causal effect, you could call it a causal. You could just like use the language of causality in a deep learning paper. It's not actually like addressing causality in any kind of sound way, and fool a reviewer, but not necessarily be doing it. And so, I tend to think that like a lot of these other problems are kind of more foundational. Like they're not problems where like we know how to evaluate systems. Let's have people try stuff and whatever. They're problems where, so I'll give you an example. Like in, you know, um, the distribution shift world. I mean, I think a handful of things people are doing that are a little bit more interesting or sound or actually um, giving a path forward. There's a group at Stanford, some of Percy's students, uh, Shiori and Pongwei among them, put together this really expansive benchmark called Wilds, and it's a like a collection across a whole lot of different application domains of a whole lot of different settings where you have some kind of subpopulation shift or some other kind of distribution shift. And it provides like a sort of unified resource for a whole bunch of settings. Again, like you still need to have some kind of, you can't just like use the data set and say, oh, I tried this thing in this one domain and it generalized well to these two others, therefore it's robust. But at least it gives you some um, like unified resource for asking a question. Like if you compare to the world where basically people are just saying like, I have pictures of MNIST images and then MNIST images on funky backgrounds. I think it's like a big advance towards like a nice sanity check and putting people in touch with the sorts of problems that are arising in the real world. Um, there's one formulation of these domain adaptation settings is that there's a version called domain generalization. Um, and here it's like sort of saying I have like a bunch of different environments that I've collected data from, and now I have, I want to generalize well to target environments, possibly using the fact that like I can look at the different source environments that I've had, and they're actually marked out as different environments. I could try to see something like what's stable versus unstable across environments. And there've been some interesting papers. Um, by the way, before we met, I pinged some of my students, be like, "What do you think are some of the interesting papers?" So I want to give some credit to my students who are now like the extension of my memory. So my student Sarah pointed out there's a lot of interesting work where you have a whole lot of methods that are proposed, but it turns out that if you set up a really rigorous baseline, and there's some papers, some from CMU from our friend Alon Rosenfeld and his advisor Andrei Rostesky, some from David Lopez-Paz at FAIR, but where they've shown things that like for a lot of these setups, it's really, really hard to beat like really stupid baselines, like just dump the data together and just do ERM on it, like just train on all the data together and don't use the environmental labels in any sophisticated way. In our own lab, my student Sarab's been making a lot of progress on these distribution shift problems, and we have some results that we've been excited about, like among other things, working out when you're presented with, you've trained on data from, you have some classes you've seen before, and then suddenly at test time, you have some data that shows up from some additional class that like you never saw before. Can you actually on the fly look at, this previously seen data from some classes and now additional data from some unknown class and identify like, oh, I say precisely what fraction of the new data is from some previously unseen class, and even develop a classifier that can now start predicting it. So it can say, oh, I think these samples have this probability of belonging to that class. So you'd imagine that like in the context of like a model monitoring pipeline, you'd eventually like to live in that world where if the world changes in some way, the model could come back to you and say, hey, I think with high probability, like, at least 20% of your new data actually belongs to some new class that you've never seen before. And here are some examples that I think belong to that class. And then you could sort of, take some kind of corrective action if you think that the model's wrong. That's on the robustness side. On the causality side, and I got some of these tips from my student Shantanu of some of the work that we've been talking about and going over. I think causality research is really exciting because it actually gets to the question we care about, which is like, what would happen if I did this versus what would have happened if I were just a passive observer watching the decisions get made as they always are. And causal inference gives like a philosophically coherent way for answering those kinds of questions. But the danger is that those answers are almost always predicated on some pretty strong assumptions that like I can learn this like the parameters of my causal model, but the structure of the causal model is given like a priori, and I know it exactly, and there's no unobserved confounding that can make all my results invalid. And so there's a lot of interesting things happening. Among them, there's some folks like Carlos Ginelli, who just started a faculty job in the statistics department at UW, has been doing a lot of interesting work on sensitivity analysis. So if there's measurement error, or if there's some omitted variable bias or something, just how, like frameworks for being able to say just how much would there have to be for me to change my causal conclusion, right? So getting towards like, I'm not just saying, oh, if I'm nailing all these ridiculously precise assumptions about how the world is, then this is the answer to your causal query. But saying like, this is how far off those assumptions would have to be for like me to like have to totally change my mind. Eric Chechen is a researcher at Wharton, a statistician who does a lot of exciting work in this area. And Shantanu hit me to a paper that he's doing, which addresses a specific problem of, people often make this assumption that there's no unobserved confounding. And, that is such a strong assumption because it's like, even if you have the right confounder, if you just measure it in a slightly noisy way, then there's unobserved confounding. And so he's gotten to this formulation we call proximal causal learning. And it's like you can allow that, okay, I have some proxies for the underlying confounders, but they're not perfect proxies. And what can I do in that situation? And finally, one thing on the causal inference side that I've been really excited about is, a whole lot of machine learning just sort of takes this stance, which is like, I've got this set of variables, and I've got a collection of examples. It's like something like, my data looks something like a table. Now it could be kind of complicated because if it's like text, the different documents could be different length, but it's sort of the typical formulations that people work with don't usually allow for the setting where it's like, oh, I have a collection of a bunch of different data sets, and I observe this thing in this data set and this other thing in that data set. But I feel like a lot of real world decision making is actually governed by that kind of process. I think we've all gotten a little bit of a crash course in this from just watching like the like COVID response like unfold in the public eye, and it's like, oh, I've got this data from the CDC, but it has these features, but it doesn't, it tells you how many reported cases, but it doesn't tell you how many tests are run, But oh, I have this other data from the manufacturers of diagnostic equipment, and that data actually tells me what fraction of tests are positive, not just what number of tests are positive. And I have this other data from, the local municipalities. And so you get to these questions where it's like, if I have some question where, I think very often we have queries, especially in economics, this comes up, they call them like data fusion type problems, but where like the answer can't come like directly. Like I have no one data set that can necessarily answer my query, but I have a whole bunch of different data sets. And it's possible that if I combine them intelligently, I could sort of like triangulate to the answer to the question that I have.
We talk about that on the infrastructure side as well. Is there kind of terminology evolving on the machine learning side for thinking about problems like this? For some reason, it also calls to mind graphical kinds of things, in that you'd imagine some kind of connectiveness in the data and the way they're represented to one another.
Well, in the econ world, they call these like data fusion problems. And someone who's done some really interesting work on that from like the AI ML side is a researcher named Elias Barenboim. So he's a professor at Columbia, and he was Yuta Pearl's grad student, and now he's a prof in his own right, doing a bunch of, I think, a lot of the super exciting work in this area. And he's gotten to these sort of questions where like he has this paper from I don't know if maybe it was technically 2020, but I read it in 21, so we can call it 2021. But on an algorithm for what he calls like the general identifiability problem. So it's not just saying like, oh, I've got this one data set. Is this thing, can I answer my causal query? But it's like, oh, I've got this collection of data sets, and in this data set, these variables are observed, and this other set, this other variable is observed, and maybe this data set was collected by someone doing a particular kind of experiment on one of the variables, and this other, so it's like I might have different data sets from different experiments. They're not even necessarily just different views of like the same data. One of them, someone was intervening in some way. But it's if you kind of have this collection of data sets and some underlying causal structure, now can you tell me precisely how can I combine all these data sets to answer the question that you have? Or I guess like, with causal questions, always the first step is it possible to identify, the answer to the question that you have based on the data that's available? And then, if you can, well, give me the formula such that if I plug in the data from these different data sets, I could, it would give me that estimate. So it's like, is it estimable? And if so, like, how do I produce such an estimate? Yeah, so there's, I think these are general exciting areas. There's also a lot of work happening now in causal discovery. So this is a really ambitious problem because, so in causal inference, you basically say, I know the structure of the causal graph. Like I know which variables potentially cause which other variables, but I just don't know the functions that determine, so it's like X, X and Y together influence Z. I don't know what is the function by which the values of X and Y determine Z, but I know that like Z listens to X and Y. Like if I were to intervene on X, that could potentially change the value of Z. Whereas if I were to intervene on Z, it wouldn't change the value of X, right? And so if you have this kind of structure, causal inference says, well, how do I like figure out, basically what are those functions so that I could then answer a causal query? But there's like a sort of like, and that by itself is super hard. And we always never agree on causal effects because it's like, well, if you assume the graph looks like this and it's slightly different, or then all bets are off. Causal discovery basically says, what if I don't even know the graph a priori, or I have some partial knowledge of the graph, but I don't actually know fully which arrows go from which variables to which other variables. So in that case, you ask this question of like, well, when is it possible to recover the graph? And in general, you can only recover the graph up to like something called an equivalence class. But now there's a whole bunch of other papers, and I don't have all the links, so I could send them to you offline. But things where they start asking questions that says, okay, like, well, if I'm able to use causal discovery to get the graph up to like equivalence, well, now I can ask a question like, what set of experiments should I run in what order to, as efficiently as possible, resolve any lingering ambiguities? So like, right, just the observational data might at least tell me something like certain variables aren't connected to other variables. And I'm able to orient for some edges in the graph, like which direction do they point, but others I can't, but then, the hope of causal discovery is to be able to additionally do that. So that's one, exciting thing. And my student Charrington, who's been working a lot in that area, so we have a paper that gets at this question of if you have to make these decisions about, kind of like I was telling you before, if you have different data sets and by combining them, you can answer a question, but not necessarily by using one of them alone. Or even if you can combine them to answer the question, there's still an unresolved question of how much data should I collect from this source versus that source in order to like as efficiently as possible pin down the causal effect. We've been working on that problem of basically how do I like, imagine you're working at a company and you have some third party data provider that charges you for, I have to pay this much per 1,000 examples, right? Like, how would I make the decision sequentially of like, okay, based on what I know now, which data source should I query next and for how many samples? And then, okay, now I update my belief, I make a subsequent decision, which I think this decision process is always going on in the background, right? Like if you're a company that's buying data from people or going out and actively, doing some kind of monitoring effort, data collection, you're making decisions on the fly about, I want to collect data from here. Oh, now I know something I didn't know before. This is going to guide my decision of what to collect next. But we don't usually formally model that process. We usually sort of assume the data is already there and then focus on how do you estimate, something given that the data is there. So, yeah, those are some more stuff I'm excited about in that direction. And I think on the fairness side, I think one way that things are maturing is that people have been posing these questions in ways that are maybe, I don't know if you're familiar with this philosopher Charles Mills, who passed away recently. Yeah, so he's this great like moral and political philosopher, and he writes about um, this sort of like ideal approach to theorizing about questions of justice, and in and I think it, and my student, I had a postdoc who graduated, Stina Fazlpour, who's now a professor at Northeastern. But we wrote a paper like a couple of years ago, just making a connection between what's going on in ML and this sort of framing of ideal versus non-ideal theorizing about justice that comes from, among other folks, Charles Mills. But he has this point that when you start posing like a question about equity or a question about justice as a sort of like technical problem, and you make up a toy model. There's this danger that you sort of highlight as like salient and relevant those parts of the problem that are captured by like your toy model, and you relegate as like not even of academic consideration everything that doesn't show up in your model, right? So I think that, and the danger here is that like if the things that you're just like completely forgetting about are actually like the everything that really matters, then
Right.
you wind up in this situation where you could do a lot of academic tinkering and you could even develop like elegant mathematical theories, but they have almost nothing to say about the underlying question of justice that you care about. And I think this is sort of the situation that we've been in to some degree. And it's not to implicate everyone, but it's to say like the main thing, right? Is that we've been posing these questions of equity in the form of like, say I have a data set, say I have a particular feature. Let me just sort of start enumerating different things that should be equal, and then saying, oh, well, it's not possible to make them all equal simultaneously. So let's either just like naively pick one and then flesh out an algorithm for it, or just kind of like pine about how fairness is impossible. Um, and I think like what gets lost in that whole kind of discussion is that it's almost all of it is like taking for granted just I've got a data set, there's a bunch of anonymous features. I don't really say anything about what they actually mean or what real world processes they correspond to or how disparities arise and how um, that consideration really bears on what is sort of the appropriate uh, response from a standpoint of like affecting justice. Like when is it, we don't look at every single, like we don't look at I don't know. If you don't look at like the Major League Baseball, for example, and say like, oh well, I noticed there are more players from some country that than from some other countries, relative to their, and say like, okay, let me just equalize it instead of quota system. But it's also because you don't believe that like I don't know, say some country that like excels in baseball, like Puerto Rico or so. You don't think they've been giving an unfair advantage in getting to the major leagues or something. And so like this whole backstory of like what actually are um, the what actually do these variables mean, and to the extent that there are disparities reflected in the data, like um, where do they come from, and how do they correspond to some political some coherent political stance or theory that sort of makes a straight line from that to who has who has a responsibility to remediate it. These are like fundamentally the concerns that we sort of always have when we speak, I think, in the law or in a broader sense about questions of justice. That for some reason I think there's something I think maybe just about the fact that it's a new field or something like that, but that for some reason have been just kind of completely sidelined, or completely is a strong word, but by like the main branch of fairness research. And I think there's a number of people who are doing interesting work here to try to actually ask like the critical questions. And I think like Lily Hu and Issa Kohler Hausman are two people who I think just have been like kind of asking the right kinds of questions for a while, and kind of framing that critique in a way that I think is what's so rare. It's like both really understands what's happening in like the sort of fair ML world, and also really understands the sort of context and like the people who actually understand ethics and actually understand like legal principles of justice, and are I think able to speak from some degree of authority to sort of what's missing in the way we're posing those questions and tackling them.
Before you jump into their work, the things that come to mind for me are this idea of techno solutionism being part of the problem. Like we're trying to throw technology at the problems that technology is creating for us. That
Yeah, we talked about that a couple of years ago.
we did, and also there's kind of a nod in the way you talked about the problem of fairness to causality. And when we all got really excited about causality a couple of years ago, and I think it was that same NeurIPS was when everyone left excited about causality. Like it was supposed to be the savior of fairness, and it was applying causal modeling to machine learning more broadly was going to give us transparency, give us fairness, give us interpretability, and break open all of the black boxes and all of that. Like where's that?
And I think I couldn't more highly recommend Issa and Lily's work here. That I think there's a handful of works. There's some work by Elias Barenboim and by Ilya Spitzer that has, and before some earlier work by like Matt Kuzner that sort of pose different um, notions or of that are like within a causal framing, kind of like coming out of like Pearl's causal modeling. So some notions of like the earliest versions of that say something like, well, there's a lot of different versions, but someone wants to say something like, okay, it's not just a question of is race or gender or whatever is considered as protected attribute, does it turn out to be correlated with some outcome? We want to ask some question of like, is it what causes the outcome? And there's a way that like these questions have been paused, and it's actually, the causal framing is not unique to machine learning. It's actually something that I think like the legal scholarship itself often expresses things in causal terms, right? Um, you know, and before them, I think like economists, for example, like there's a famous experiments, right, where people say, well, we sent like the resume experiment that I think Sindel Milenithan and some others ran, where they randomized names to be tip more likely sort of like Black American sounding as well as more likely to be white American sounding as, and then they send the resumes to people and they measure the response. And it's an interesting experiment. It's certainly like uh, valuable research. And the fact that there's in certain contexts a difference in the response rates, like, does jump out as problematic, right? On the other hand, if you sent them out and there was no difference in response rates, should we conclude in the other direction, like, oh, there's nothing wrong, right? And I think the answer is, obviously different people will have different opinions, and the answer might be answered different in different contexts. But I think that there's a lot of contexts in which I think many of us or most of us would say that that's not necessarily the case, right? For example, if right, like if you're like, oh, because it's like, what does it mean to just change the name, right? It's like I could change your name, but and that wouldn't make a difference. But if I changed what college you went to, from say like HBCU to say some other school, and that made a difference, even if your name by itself, conditioned on everything else, didn't make a difference. So there's this notion that's baked into a lot of literature that tries to pose questions about discrimination through a causal lens that sort of tends to adopt a rather like narrow notion of what could constitute discrimination as like the direct effect of some attribute, like the direct effect of gender, the direct effect of race on a decision. And the problem is that, well, what about like all of these sort of potentially indirect effects that could still be, if someone were to make a decision based on some factor that is super correlated with race and also irrelevant to the decision otherwise, well, like, would you say that that's not discrimination? And so there's this, then there's some work by Elias Berenbaum and Ilya Spitzer, which is, I think, a sort of step, at least conceptually, in a more interesting direction. Whereas what they try to do is sort of, if you have like a causal model over all the variables, you could say something like, well, let me disentangle the how the effect of some attribute of interest, whether it's race or gender, comes to influence some outcome of interest along all the different sort of plausible causal paths that it may take. And I could sort of attribute to what extent is this, influencing the outcome via that variable versus via this path versus via this other path. Now, keep in mind though, like that sort of, I think what's cool about it is it's like a thinking tool. Like in practice, do we actually expect that we would have a causal model that captures all the variables of interest and actually says exactly, we would know precisely which variables influence every variable that goes from somebody's gender, to whether or not they got hired, we'd be able to, like, we're going to trace like over what scale, like over the scope of someone's entire life. We're going to, build into our graph every opportunity, right? Every decision, every opportunity that someone was given or not given on that account, like that we're going to have a graph that is so rich as to capture all of that. It seems unlikely, but at least it gives you maybe like a thinking tool as like, okay, at least I can conceptualize and step back and think about the fact that there are these. But among other things, it outsources the normative work, right? At the end of the day, presumably the reason to disambiguate these different pathways is to say someone believes that, they usually put it as like in the terms of like some paths are permissible, like maybe they run through like unambiguous qualifications for the position being hired for, versus other paths are sort of like impermissible paths because all they're really doing is telegraphing information, but they're not actually influencing. They're not actually say relevant to the job qualifications or whatever the context is. But they're still outsourcing the normative work of someone. Well, someone has to go and say which paths are permissible and which paths are impermissible. And Lily has a really sharp critique. She also has a nice set of um, blog posts that are called like disparate causes, I believe, on this blog Phenomenal World. But it goes into this problem kind of critically, and among other things, you know, getting at this question of what we call like a direct effect or an indirect effect is partly an artifact of the representation that we have. And there are some causal questions where, for any kind of process that we describe, there's multiple different valid causal representations conceivably, right? Because you can always like zoom into, if I have this variable and this variable and an edge between them, I can always zoom into it and say, oh, like it's not just that like someone's college influences their internship. It's actually their college influences this subtle decision that's made by some recruiter, which influences this, which influences that. And so you can always zoom into it and sort of bring more into focus, and whether or not someone would like look, now like a very generic question, like what is the average treatment effect? Maybe as long as you had, whether you had a very sort of granular or a very sort of, coarse representation of some process, if they're both valid, you'll have the same answer for a question like that. But this question about like, what are the pathways taken is sort of like, and are they permissible or not, is sort of an artifact partly of at what resolution do you zoom into this process and do you capture it. And something might look okay, if you zoom way out and you subsume a whole lot of mediators into just like an arrow. But if you zoom in closely and you knew more about how that process took place, then maybe you would say, oh, this isn't kosher. So I think, at a high level, I think that like causality gives us like a set of thinking tools for thinking critically about some of these problems, and they are maybe in some way like a partial step in the right direction. um but at the same time, I don't think it's like a magic bullet that like sort of addresses all questions of fairness or justice or discrimination. And I think that often, they're that the sort of like model that was sufficiently rich to be able to, even if you believe that they were like, you wouldn't actually have, you know you wouldn't actually be able to like produce the causal model so that you could fully resolve those questions. And I think one nice point that Lily makes, and I think it might have been uh, um, in joint work with Issa, but I remember one of the points is that, I think that there's a lot of times like a danger is that it could be a little bit of a distraction. If you said this like heroic amount of, I have to know every single variable and every single thing and estimate every single relation, and before I can make any kind of conclusion about whether there's discrimination, that might not actually be necessary, and it's not in general what we do. I think there are situations where we can size up, um, at a bird's eye view, that there's some fundamental like inequity in society, and conclude that we have some responsibility to do something about it, and that doesn't need to be contingent upon saying that like I've exactly estimated every single possible, causal functional on the pathway, of every single factor that plays any role in, on the path to some decision that's made about someone in their life. That might set like a, um at the end of the day, like too high a bar that, you kind of, um I think we're able to recognize cases of discrimination, and plenty of cases where we're not able to do this kind of like, you know um Herculean like numerical feat.
Let's maybe shift gears and talk a little bit about use cases or application areas that have made notable progress in 2021. Anything come to mind there?
You know, well, look, one obvious one, and as much as I might, be kind of called on as a contrarian, but like, uh, one where I think got to give some credit is, I think, um, AlphaFold from DeepMind. Like I'm not a protein folding expert, but I know some people that are not just like gullible deep learning boosters, who do work in the area. And as far as I can tell, it's like actually a pretty significant um, leap forward. That it's work that could very well have won like a significant science prize, on like that level of accomplishment. Um, and that's a little bit hearsay in that like I'm not an expert in protein folding, but as far as I understand it, it really is a legitimate significant contribution, and I think an area where maybe deep learning wasn't quite as inlined as a essential tool. So that's certainly um, a use case. I think you're starting to see um, a lot of the use cases that were maybe obvious ones, but not necessarily um, for example, like radiology is sort of like an obvious initial thing because, and harkening back to like our earlier conversation about the difference between prediction and decision, well, part of why radiology is like people see it as like this big target is that, um, there are certain roles of the radiologist where they really are involved in decision making and the recognition is part of a weird, it's like an interventional radiology. But there are also lots of people who literally are looking at images and making classifications. And medical imaging is a case like a diagnostic kind of imaging, right? And I think that's a case where we've known since the moment, the kind of big image recognition results started hitting in say 2012, 2013, that radiology was a potential target. And you had some maybe overly optimistic statements from like Jeff Hinton, like if you're in medical school now, do not specialize in radiology. It hasn't quite gotten to that point. It hasn't taken the radiologist out of the loop. But I've been chatting with a lot of radiologists recently, and I've been surprised to find, well, sort of two things. One, on one side, that some of the systems really are quite good, and you actually have some systems being deployed already, actually piping information into patient records. Um, and at the same time, that I think some of the problems that we discussed earlier about what can go wrong are happening on the ground. And you do have a situation where, for example, systems that work well on one set of equipment are not performing well on some new scanner, which it's sufficiently similar to all the other scanners that a human radiologist would have no problem.
Right.
And these are not adversarial examples. Nobody's out there designing a scanner. There's not like there's like a radiologist on the team who's like, I'm gonna build a scanner that just fucks
Beat
up all
the
the previous, fucks all the deep learning, so that way we can like keep our jobs. So I think you sort of have both a moment of the technology actually kind of like making landfall,
Mhm.
but I think you also have some moment of like the rubber hitting the road and people sort of seeing up front, some up close, some of the ways in which the technology is brittle and dangerous.
Yeah. Yeah.
And I think that largely, like, this might be like an unsexy story because in some ways it's like what's like the big sexy application, but I think largely the story now, and I think that overall the biggest, like if I were to like take a bird's eye view of the economy and just like I'm just watching like what is AI doing, I think, right, the story of like 2014, 2015 is like these new use cases, like fundamental new things popping up, like things we weren't doing with deep learning, suddenly like machine translation, people swapping out the old guts and sticking in the deep learning systems. And suddenly like every single mobile phone having the capacity to run some kind of small deep learning model because it's being used for recognizing objects in the cameras and doing the face recognition that unlocks your phone and all of that. I think the bigger story of the last couple of years has been more on the side of like deployment and like diffusion and like maturity of the like operations around ML. Like I
Mhm.
notice more and more companies that like their pain point isn't that they need someone who could train a model. Their pain point is they need an ML ops person. They need someone who can actually keep the crap running day in, day out. That someone who knows, it's like there's some specialized set. It's not, it's like a pure like ML researcher, like someone like me. Then like I don't have this skill set. I haven't spent my life in like, there's a real serious discipline in like keeping software working day in day out. Like the people, it's amazing what we could do when you see companies that like have a software that product that like 400 million people use every day, and they like go 7 years without a single hour of downtime. It's absolutely bonkers how difficult that is. And machine learning is throws in a whole, I think researchers don't have that skill, but machine learning throws in like a weird set of complications because there's all kinds of ways that things can go wrong, even if there aren't software bugs. And so they need to understand something about enough about statistics to have some sense of what could go wrong and ways that you need to model things that aren't software glitches. They're like the world changing glitches. There's like the world is the bug, even if everything's coded precisely, and need to be able to interface back and forth between like software developers, ML engineers,
Yeah.
and researchers. So I think like the maturity of ML ops, and also just broadly like the use of ML, not just in I think there was a moment, right, when there was Google, Amazon, Facebook, Microsoft, and I don't know if you ever read this, but like I wrote this like satire bit, just because like when everyone was making a big deal about like, oh, whatever professor left to go to whatever company and this is their salary, and they were kind of writing about it like almost like football players getting traded or something. And so I wrote this stupid post that was just like announcing that I had been hired as like the intergalactic head of machine learning by Johnson and Johnson or something, and I'd be, for some, astronomical sum. And it was just a stupid joke. But the funny thing was like a year later, I forget where I was, and I met someone and they worked at like Johnson and Johnson AI research, right? And I think that this is part of like what's going on now is that
Yeah.
like there was a moment in time, I'm sure, like I'm making this up. I research it before but this is what you come here to speak from academic authority, just make up crap on your podcast. Uh, I'm sure there was a moment in time where like there were only a small number of like elite tech firms that were using like modern SQL databases.
Yeah.
When it was fresh, I think it was at IBM when it was developed, but there's probably a moment where this is like a really hot, fundamentally new technology that really changes business operations at places. And there were like a handful of like super technical firms that knew how to do it. And now
Yeah.
it's like the most boring technical firm in the world uses SQL.
Right.
And I think that this is a huge part of what's happening in AI if you were to size up like the commercial environment. So I think there are exciting startups that are using this technology in new ways. There are, interesting things going on at like the sexy tech companies. But I think there's a lot of like, there's no company that you go to, whether it's like I'm sure if you went to like a waste management company, like they're finding, they're using AI for something or forecasting demand or trying to figure out how to route their trucks or something.
Mm-hmm.
And I think that like this sort of just general like progression of AI from like a luxury good to a commodity is like an essential part of what's going on.
Yeah.
And like the fact that like every company has this is becoming their concern. And I think part and parcel of that is the way that the tooling is getting better and better and better. A whole lot of companies, like what are they offering? It's like uh, things that make it that like the stuff that everyone's already been doing for a while that anyone could do it, right? And it's easy to track, and it's easy to organize. And like I think this movement of like AI from a concern of like what's the new model to like what is like a stable workflow that we can adopt such that a company that can't spend $500,000 per engineer can still use this technology like successfully and profitably. I think that's a major part of the story of like the commercial application of AI right now. And it's kind of like it's a pretty unsexy story maybe of just like, oh, this is just becoming right. But I think this is what happens to everything, right? Like at some
Maybe an
point, like,
unsexy story if you're a AI researcher, but if you're in ML ops, it's pretty cool. And
oh
there's
yeah,
a lot
absolutely.
of really cool stuff happening in that field for
And there's
sure.
a and there's like a lot more jobs at every company in the world together than there is at like whatever it is, like Apple, Microsoft, Amazon, Facebook, whatever. So I think that move to
Before we run out of time, I'd love to have you kind of dust off the crystal ball a little bit more and kind of share some of your predictions for the upcoming years. We've talked a little bit about where you'd swing the bat from a research perspective, but how do you think 2022, with the backdrop of kind of the I don't know if you'd call it a cooling or a slowing or a boringification or whatever you'd want to call it. Like, are there innovations that are, you kind of see the silhouette emerging from the shadows, and you think something's there?
Right, the Kool-Aid. It's not. The funny thing about that is it's not like it's all cooling or it's all heating up. It's like I think the coolest or weirdest, interesting thing about it is that it's like whenever you sum up something like a complex phenomena with like a single number, it's like you lose a lot of information. I think it's like right, it's sort of like more like fall of the Roman Empire, right? It's like Rome's all right, like Rome is still partying and like the borders are still expanding, but you also have like like you have like cities being lost and whole countries going off the map, and it's like I think that's happening, right? Like you have like Uber AI shutting down AI research. You have like hiring freezes at major companies, the big leaders like having major hiring freezes, not offering the kinds of salaries in 2022 that they were offering in 2018 to like kind of like well-known researchers. And at the same time, you have like whole companies where like the shockwave hasn't even hit them yet, and they're like first getting into the like major health systems starting to adopt like deep learning and I think that yeah, there's that going on. If I had to predict what's going to happen, like I'm gonna double down on uh, decision making. So I think something that I'm already seeing a lot of is like you could think of like a few things came together that made AI so hot, which is like one was suddenly the fact that like the existence of easily queryable, well organized, curated data at every single firm in the world. The fact that like health companies suddenly using electronic health records, every company being basically an internet company, everyone having a digital trace of all their customer interactions. Now, we can get into a separate like normative point about whether we want to live in that world or like whether we're irked by the surveillance state. But from like an economic standpoint, that happened together with like advances in both the tooling and algorithms around statistical modeling. And so the question became, we have this data, we have statistical tools. How do we do this like analytics on the data, right? But there's another side, which is like how do we use the data to guide actions? And I think people, I think one thing that is underutilized by most firms, and I think only a small number of people are really sophisticated about it, is is really focusing on this like the decision problem. And part of that is offline causal inference, which is some of the stuff we were talking about. Like, how can I use some causal background knowledge together with the data that I have to infer a causal effect and then use that to guide a decision? But a huge part of that is experimentation. And I think that this is a huge thing that not enough companies do, that you're going to start seeing become obviously like Amazon has the what they call it, like web labs, where the Google like does randomized controlled trials for which shade of green the G should be in Google or something. But I think most companies grossly underutilize experimentation, like really methodical experiments, because that plays into the data picture.
Online experiments in particular?
Well, online, not necessarily in the sense. I mean, I think online is part of, in a sense of like, doing like reinforcement learning or having like a policy that's adaptive as you're getting the results. But even experimenting at all, right? Like just like we've been guiding. If you look at how we guide personalized decisions, it's often in the context of I just take passively collected traces of people's data. I do some kind of latent factor analysis or whatever to build a recommender system, versus actually I'm going to randomize choices and try to estimate the sort of like potentially like heterogeneous treatment effects of how different people will respond differently to different things, but actually to estimate the effects on um, whether it's people's behavior or whatever. I don't mean this is sort of like sound like I'm advising that we like willy nilly experiment on people without thinking about the considerations or which decisions or which experiments are potentially like of ethical import. And obviously, there's a lot that there's a lot of considerations that need to go into how you do that and doing it right. Um, but yeah, I think that you know the reckoning we're seeing, I think, is over and over again is like people claiming the AI is gonna, it's gonna personalize this, personalize that. It's gonna lead you to make all these different decisions in better ways. And then people find like, oh, I just naively trained a predictive model, came up with some heuristic for how to operationalize that as a decision, and something didn't go as planned. And I think that people actually getting more into this world of both using offline, kind of causal inference on observational data, but also actually experimenting in the real world and developing more mature processes for saying how do I test hypotheses, how do I see what the impacts are of different actions that I have. I think that that's going to become more and more and more important, and you're going to start seeing the like hiring focus, and just like where teams start moving, you know towards those kinds of problems. And again, I don't think this is like overnight. You're going to go from people like hiring 90%, deep learning, like PyTorch jockeys to like 90% hiring, experts in like, bounded algorithms and causal inference. But I do think that there's a shift here. I'm seeing it at every level. I'm seeing it in what looks, interesting among new students, what looks interesting among folks hitting the hiring market. I think that this sort of intersection of like, um, CS, operations research, economics, and bringing to bear like, tools of predictive modeling that we've gotten, but also um, um, more sophisticated processes of experimentation and estimating causal effects and principles of just guiding, intelligent decision making. um, I see I think there's like a growing up process happening there. And um, I think the other thing though is one thing I'd add on, and this is not like a specific prediction but a meta prediction, is the like the internet, like web 2.0, web 3.0, whatever the hell we're doing, like very little, there's a lot of new stuff that we're seeing in like the way companies are behaving and the way they're interacting with people, that isn't technologically new, right? There's a lot of stuff that like you could have done from the late 1990s. um, the tooling wasn't as there, which restricted how many people could develop it. um, but it was something else. It was something about like, there was a capability that came, and a few people have figured out some very like some early players that figured out like, how to conquer e-commerce, like Amazon, whatever. But it took a long time before you got to Uber, right? And so there's certain innovations there that were like, it's like there were a bunch of pieces that need to fit together, like a certain understanding of like markets, or a certain understanding of like usage patterns of phones with a technological capability that had been there all along. And I think that like there's a kind of like innovation in deployment that doesn't actually correspond. Like I think when people have been stoked about ML recently, right? It's been like, oh, BERT is like good at classifying text, or like seek to seek, LSTMs, and then transformers are good at this one thing. There's like single purpose models. But like I'll give you an example. So I'm an advisor for a company, so it's full COI. I'm an advisor for a company called Bridge AI. And a bridge is a company that like is sitting between like doctors and the patients, and sitting in this like interaction where patients, it turns out patients are busy recording their visits on their cell phones, and they're doing this already, sometimes surreptitiously, sometimes with the doctor's consent. It may or may not be wiretapping, depending upon like what your particular state's like, two party. So their idea was like, let's inline this as like a normal part of the doctor patient interaction. Like, let's have permission, let's have both parties get in, they'll agree to record the conversation, they'll pull out a bridge, and then they record it. And there's all kinds of different things you could do, right? Like you can help the doctor to draft a summary of the visit, you can help the patient to understand like, oh, like, don't forget, like you mentioned that you would be starting this new medication, have you picked it up, or have you called in that prescription, or did you schedule out this follow-up? So there's like a million different places to plug in models, and any one of them by itself may or may not be like, a single purpose like major innovation. But the ways that you can mix and match these, like, okay, I've got the conversation, I've got to send it to an ASR model, I get back the text, of the text, I need to flag out like, well, what are the relevant or salient parts of the conversation? How do I then take that, turn it into like an interface feature that, provides some value or makes things useful to the patient? And I think that like a lot of things, like when Alexa works really well, right? Or Google Home or any of these things, when it works really well, it's usually not because there's one model that's like magnificent. It's like the magic is in the clever way that they stitch together, some astute observations about what are the common interaction patterns, together with like what are the right little places you could patch in machine learning, and the right ways that you can like patch in some intelligent heuristics and rules around it, such that like you know you have like an end-to-end product that feels like it's magic, right? Um, Shazam even is a little bit like that. Like one of these things where like there's a few like a little heuristics where if you start thinking, how do I decompose this into like something that works? It's like you can make a pipeline where every single step of it's kind of simple, but like the end result is something where it feels a little bit magical, right? And I think that like this is going to be I think a major part of this is like I think we've been looking at like people who are really good at building single purpose models, then turning that into a big startup, and or trying to parlay that into a startup. And I think there will be some amount of like the single purpose models are mature and they'll get a little bit better. But what's maybe underexplored a bit are ways that you mix and match models together with cool interaction patterns and some clever understanding of like what people want and what data is available, etc., to build like kind of user experiences that maybe under the hood are invoking like seven different models in seven different contexts, and but it's like kind of hidden from the user in a clever way where it just feels like you're having like it adds up to a new capability that no one model or piece of software like by itself would provide. And so I do think that there is some element of this you know like we've built a bunch of cool Legos and we haven't given people that many years to like instead of like, some innovation comes from like I designed a new Lego piece, but like I think a lot of innovation will come from people that are, you know, don't have to be like have like off the charts skills at building Legos, but they have a kind of design sense for, what are cool ways to put them together.
I think it's a natural consequence of the broader maturity conversation we've been having, right? The Lego pieces are, not that we've come up with every Lego piece that's ever going to be created, and there aren't some cool ones to come, but all the basic pieces required to build really cool stuff is in place, and now it's all about how do you put them together, yeah, and even more so than the pieces themselves, the tools to easily put them in place. You've got your Hugging Faces, you've got your MLOps tools. Like it's a great time to be a builder.
Right. Yeah. It also like it takes some of that work away that it allows you to focus. Right. I think music's like that a little bit, right? Like, there's this way, like when you're learning an instrument and you're like, I gotta practice articulation, I gotta practice rudiments, I gotta practice scales, I gotta do this, and you're sitting here going, and then you're playing this kind of shit over and over and over again when you're like 10, 11, 12, 13, 14 years old. But you get to some point where like maybe you still practice like that 1 hour a day, but when you go to play, you're not even thinking at that level at all. Like it's not, and I think there is some element of that, of like people using machine learning recently have been thinking like just like how do I get the data and train a single model? And I think once you have a lot of these contexts where maybe you don't even need to train a model, maybe there's an off-the-shelf model that's sufficiently good at this task, going to work better than anything you could train, even if you're applying it sort of on slightly different domain shifted data, right? Then you start getting to this point where um, right, like the difference between like a great artist and like a super boring artist isn't that like the great artist is better at scales. It's not at that point. Right. It's not like oh like Miles Davis played like better. Played like cleaner scales than like I don't know.
He's state of the art at staying on key or something like that. It's not like that, right?
Yeah. So I think there's a lot of innovation to be had on that side.
Yeah. Awesome. Awesome. Well, Zach, it has been wonderful catching up. Let's make sure it's not 2 years until the next time.
Yeah, right. Who knows what pandemic will be in full swing by that time?
Awesome. Well, thanks so much for helping us reflect on 2021 and the ML and DL domains. And catch you next time.
Yeah, thanks for having me, Sam. Great to see you.